All right, welcome. Today, we are going to unpack one of the most powerful ideas in all of math. It's a concept that lets us see the world not just as a series of still photos, but as something in constant, flowing motion. We're going to unlock the secret of instantaneous change.
So let's just dive right in with a question you've probably never really stopped to think about. You're driving, you glance down at your dashboard. How does your speedometer know how fast you're going at that exact instant? I mean, it's not your average speed over the last 10 seconds, it's your speed right now. How is that even possible to measure?
And that question right there, that gets us to the very heart of our topic today, this whole problem of instantaneous change. See, it's easy to talk about how much something has changed over an hour or even a minute, but how do you measure change in a single, fleeting instant that has no duration at all?
Now, have a look at this. This graph visualizes the problem perfectly. That blue line, the one that cuts through two different points, that's called a secant line. Its slope, its steepness, is your average speed over that time period. Easy enough. But that orange line, the tangent line that just kisses the curve at one single point, that represents your instantaneous speed. That's the speedometer's secret.
So here's the big puzzle. We've known how to find the slope of a line with 2 points since, basic algebra, rise over run, right? But to find the slope at a single instant, we've only got 1 point to work with, and that seems mathematically impossible. How on earth do you do it?
Well, the genius of calculus is that it starts by not even trying to be perfect. If we can't get the exact answer right away, what if we could get unbelievably close? We can start by just approximating, using the one thing we do know how to work with, that secant line.
To do that, we need a special tool. And that tool has a fancy name, the difference quotient. Now, don't worry about the name or even the formula itself just yet. All you need to know is that its entire job is to calculate the slope, the rise over the run of that secant line connecting our 2 points. It's our workhorse for getting that first good guess.
And what this shows us, which is actually a super important point, is that there's more than one way to write down that formula. You could label your points as x and a, or you could call them a and a plus some little distance h. It doesn't matter. You're doing the exact same thing, finding the slope between 2 points. And this little bit of flexibility is going to be a game changer in just a moment.
Okay, so we have our approximation, our pretty good guess. But how do we get from pretty good to absolutely perfect? Well, this is where the magic happens. This is the giant conceptual leap that gave birth to calculus.
Let's just watch this process unfold. We start here with our 2 points and the secant line connecting them. The slope of this line is a decent approximation of the slope right at our target point A, but it's not perfect. Not yet.
Now watch what happens. We take that second point, and we just start sliding it along the curve, getting it closer and closer to our first point. See how the angle of that secant line is changing? It's becoming a better and better approximation of the true steepness right at point A.
And we just keep moving it closer, until the distance between the 2 points becomes infinitesimally, ridiculously small. And right at that moment, poof, when the 2 points are basically right on top of each other, our secant line magically transforms into the tangent line. We've just found the exact slope at a single point.
This incredible idea, this process of seeing what happens as we get infinitely, mind-bendingly close to something, has a name. It's called a limit. And it is the absolute fundamental concept that makes all of calculus possible. It's how we solve the impossible problem of only having 1 point.
And now that we have this superpower of the limit, we can finally give a proper name to the thing we've been hunting for this whole time, that instantaneous rate of change.
Everyone, meet the derivative. It is, simply, the instantaneous rate of change. It is the slope of the tangent line. And how do we find it? We find it by taking the limit of our good old difference quotient, as the distance between our 2 points shrinks to nothing. See? All the pieces just snap together. Now, this is what it looks like when mathematicians write it down. Don't let the symbols freak you out. That little lim just means we're taking the limit, and that fraction, that's just our difference quotient. This is nothing more than the formal notation for that beautiful visual process we just watched happen on the graphs.
So let's actually put it to work. Say we want to find the exact slope of the curve f of x equals x squared, right at the specific point where x equals 3. Well, first, we just set up the definition of the derivative. Second, we plug in our function and our point. And third, we just do a little bit of algebra to clean things up and evaluate that limit.
And what we get is 6. At that one exact, single, infinitesimal point where x equals 3 on that curve, the slope is precisely 6. Not 5.999, not 6.001, exactly 6. That is the power of the derivative.
But finding the slope at one single point is really just the beginning. The truly amazing thing about the derivative is what happens next. It can actually tell us a story about the entire original function.
Okay, take a look at these graphs. This is so cool. On the left, the blue parabola is our original function. The orange line is its derivative. Now, notice this. Wherever the blue curve is going down, its slope is negative, right? And look, the orange derivative line is below 0. And wherever the blue curve is going up, its slope is positive, and the derivative is above 0. And at the exact bottom of the parabola, where the slope is perfectly flat, the derivative hits exactly 0.
So here's the big takeaway. The derivative isn't just a number. It's a whole new function. And its entire job, its whole purpose in life, is to tell you the story of the original function's slope at every single point along the way. It's like a slope storyteller.
And if you think that's incredible, just hold on, because the story actually has another layer to it. What happens if we treat our new derivative function like it's just any other function?
That's right, we can take its derivative. And this brings us right back to our speedometer. Think about it. The rate of change of your position, that's the derivative of position, is your velocity. But what's the rate of change of your velocity? Well, that's acceleration. So the derivative of velocity is acceleration. Its derivatives all the way down.
Which leaves us with one final, fascinating question to chew on. We know the rate of change of position is velocity. The rate of change of velocity is acceleration. So, what does the rate of change of acceleration, the derivative of acceleration, actually tell us? What does that feel like in a car? Something to think about. Thanks for watching.